The topic is aldehydes and ketones. And carboxylic acids. We'll start with aldehyde and ketones. First we'll study what is carbonyl compound. Compounds containing carbon double bond oxygen is called carbonyl compounds. The general formula for carbonyl compounds is CnH2nO. First we'll study aldehydes. In aldehydes, our carbonyl group is attached with either hydrogen in the both the side like this, or it can be one alkyl group and another hydrogen. It can be one aryl group and another hydrogen. So for aldehydes, the structure of compound, it can be like this, or for aromatic aldehydes it can be like this. Ketones. In ketones, this carbonyl group is attached with alkyl group from both the sides, or it can be one alkyl group and another aryl group, that is our benzene ring. So the structure of ketone can be like this. Now we'll study the structure of carbonyl group. In carbonyl group, carbon atom of carbonyl group is sp2 hybridized and bonded to 3 atoms. It makes 3 sigma bonds, 1, 2 and 3, with 2 carbon of alkyl or aryl group or hydrogen atom. This can be alkyl or aryl, and one side is hydrogen in aldehydes, and for ketones it can be carbon. And the third sigma bond is with oxygen. So it makes 3 sigma bond, one with alkyl group or aryl group, or one with hydrogen, or it can be carbon in case of ketone, and the third one is with oxygen. So there are 3 sigma bonds. Now the remaining unhybridized will take remaining 2p unhybridized orbital of carbon atom makes pi bond with 2p orbital of oxygen atom. This is 2p orbital of carbon and this is 2p orbital of oxygen. It will make pi bond. This is sigma, this is sigma, and this is sigma, and this is pi. So carbon is attached with oxygen atom by means of double bond. One is sigma and the another is pi bond. Now carbonyl carbon with 3 atoms attached to it lie in a same plane. These are in same plane, and the bond angle between these bonds is 120 degree, it makes trigonal coplanar structure. Its structure will be like this. This is carbon oxygen. This is sigma, sigma, sigma bond. And this is pi cloud. Pi electron cloud lies above and below of this plane. As we know, oxygen is more electronegative than carbon, so the carbon oxygen double bond is polar in nature, and electron density around this bond, electron density around the oxygen atom is increased due to its electronegative nature. So, due to electron density is more near oxygen atom, it gets partial negative charge and carbon will get partial positive charge. This causes the dipole moment in these compounds. For aldehydes, the dipole moment is 2.3 D, and for ketones it vary from 3.02 D. Now nomenclature. How we'll name these compounds? We'll start with aldehydes. Trivial name for aldehydes comes from carboxylic acid. The corresponding carboxylic acids we need to replace ic acid with aldehyde. So, if we are taking formic acid, it will become, if we are taking formic acid, it will become formaldehyde. So we need to remove ic acid and add aldehyde for its trivial name. If there are any substituent on these compounds, will give its position by alpha, beta, gamma and delta. The carbon which is directly attached to this aldehyde group will get alpha carbon. Next is beta, and the next one is gamma and delta. The carbon directly attached to this aldehyde group will get alpha position. the next one is beta, then gamma, and the next one is delta, and so on. So we'll give if any substituent is present on these carbons, we'll get alpha, then we'll name this name of substituent, and then we'll write the name of aldehyde. For IUPAC nomenclature for aldehydes, for IUPAC name, if aldehyde the name of aldehyde is given by alkane null. So for if we are taking any alkane, its name is given by, we need to remove E from this alkane and will add L as a suffix, and it will become alkane null. If we are taking methane, its corresponding aldehyde will become methanol. If we are taking ethane, we'll remove E and we'll add ethanol. For aromatic aldehydes, the aldehyde group is attached directly to the benzene ring, so its name is given by benzaldehyde. If any substituent is present on this benzene ring, its position will given by, if any substituent is present here, it will be meta. If it is here, then it is ortho. If any substituent is present here, it will be ortho, and if any substituent is present here, will be given by meta, and here will be para. So if we are taking an example, if any substituent, hydroxyl substituent is present on ortho position, its name will be given by ortho hydroxy, because hydroxy group is present on ortho position of this aldehyde, so its name will be given by orthohydroxy benzaldehyde. If carbonyl group or aldehyde group is present on side chain of this benzene ring, if it is like this, so its name will be given by phenyl. This is phenyl ring or benzene ring, phenyl ethanol. Now nomenclature of ketones. Ketones are R C double bond O R dash. Both the sides of this carbonyl group has alkyl group. It can be of same alkyl group or it may be different. In common system, or its travel name is the name of ketone is given by alkyl ketone. This is our carbonyl group, keto group, and if one side it's methyl group or another side it's ethyl group, will give name by alkyl ketone. Here it is methyl group and ethyl group, but we'll take ethyl group first as it comes first in alphabetical order. So it's ethyl, methyl, ketone, ethyl, methyl and ketone. If any substituent is present on these ketone, will give its name by alpha, alpha, beta and gamma, same as in aldehyde, but here are two chains, so one side will be given by alpha. This carbon is directly attached to this keto group or carbonyl group, so it will get alpha, this beta, then gamma and delta. The another side will get alpha dash, beta dash, gamma dash and delta dash. One side will get alpha and another side will get dash position, alpha dash, beta dash, gamma dash. So we take one example. Now we'll name, this is our keto group, this will get alpha, beta, and the another side will get alpha dash and beta dash. So its name will be alpha dash, because two chloro group is present on this alpha carbon, so 2 times alpha for one chloro group and the another alpha for another chloro group, then alpha dash for the third chloro group which is present on alpha dash position, so its name will come by alpha 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 dash trichloro, tri for 3 chlorine group, trichloro, then alkyl group. Here it is 2 carbon and this side is also 2 carbon, so 2 ethyl group, alpha alpha dash trichloro diethyl, di for 2 and for ethyl 2 carbon chain is there, so diethyl ketone. So alpha for this, another alpha for this and alpha dash for this chloro, so trichloro, alpha 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 dash trichloro di for 2 and ethyl 2 alkyl carbon alkyl group is there, so trichloro diethyl and ketone. IUPAC name for ketone group. For this method, we need to take the longest chain. Longest carbon chain is selected as a parent chain. So will number from that side where carbonyl group gets the lowest number, so it will number from this side. Here both the chains are having same number of carbons, so we can select any of these, this one also or this one also. So the longest parent chain is selected first and then chain is numbered from that side where carbonyl carbon gets lowest possible number. So from this side it is getting second position, and if we count from this side it will get 1, 2 and third position, so it will not be preferred, so we'll count from this side. So carbonyl group get second position, and then ketone is named by replacing E from alkane and adding on. So its name will come from its corresponding alkane and it will become alkanon. So if we take acetone, acetone is its trivial name, and its IUPAC name will be, it's 3 carbon compound, so its corresponding alkane will be propane and its acetone will become propanone. Now if any substituent is present on these compounds, will give its name by, we'll take this compound as our example. We'll count from this side 1, 2, 3 and 4. Here the longest chain is 4 carbon chain, and the substituent is this methyl group, which is present on third position, so its name will become 3-methyl 4 carbon, so corresponding alkane will be butane, and the position of carbonyl group is second, so butane 2 on. So its name will be 3-methyl but 2 on. Now for aromatic ketones, if we take benzene ring, then our carbonyl group, then alkyl group, so its name will be given by aceto for this, CH3CO aceto, and phenone. Or methyl phenyl ketone, if a compound is like this, if it is having 2 benzene ring, will number from this side where carbonyl group gets lowest number, so 1, 2, 3 and 4. We'll take these benzene ring as a substituent, so it will get one position, this phenyl ring is on 1 position, and 3, second benzene ring is on 3rd position, 1, 3 diphenyl butane for 4 carbon chain, and the carbonyl group is present on 2nd position, so 2 on, so its name will be 1, 3 diphenyl for 2 and butane for 4 carbon chain and 2 on for second position of this carbonyl group. Now isomerism. Isomerism in carbonyl compounds are first chain isomerism, aldehydes with 4 or more carbon atom will show this type of isomerism, and for ketones 5 or more carbon compound will show this type of isomerism. We'll take and the 4 carbon compound can be like this, or this. So its name will be butanal and its name will become methyl group will be taken as substituent. So 2-methyl propanol because it's 3 carbon compound and it's butanal. So for the formula of C4H8O compound, it can be butanal or it can be 2-methyl propanol. It's a chain isomerism because here the longest chain is 4 carbon, 1 2 3 4, and here it is 3 carbon, so it is called chain isomerism. If we take ketones, the chain isomerism can be like this. Both are 5 carbon compound, but here it is 5 carbon chain and here it is only 4 carbon chain, here it is 5 carbon chain. So its name will become pentane 3 on, and for this it will become 3-methyl. Methyl group is on 3rd carbon, 3-methyl butane 2 on. See, here it is 5 carbon chain and here it is only 4 carbon chain. So the ketones will of 5 or more carbon will show this type of isomerism. Second is position isomerism. Or here will number from the left side because carbonyl group is on the lowest position, and for this we can count from any side. This is 5 carbon chain, this is also 5 carbon chain, and its name will become pentane 2 on, and for this it will become pentane 3 on, because carbonyl group is present on second position and here it is present on third position. Now for aromatic aldehydes, aromatic aldehydes also show the position isomerism. If any substituent is present on ortho position, if it is present on meta position, and if it is present on para position, will give name. It's a tolualdehyde, so it will become ortho tolualdehyde. This is on meta position, so we'll give meta tolualdehyde, and this is on para position of aldehyde. This methyl group is present on para position, so it will be given name by para tolualdehyde. So these kind of isomerism is shown by aldehyde and ketone, and as we know, the formula for aldehyde and ketone is CnH2nO. Both the aldehydes and ketones also show the functional group isomerism. One is this and the another is this, but the general formula for them for both is same. Here it is this. If we take C3 compound, C3H6O, for ketone it will be like this, and for aldehyde it will be like this. So both are functional group isomers. Now methods of preparation. Methods of preparation for aldehyde and ketones. First, from alcohol. From alcohol we can get aldehyde ketone from many methods. First we'll take from alcohol by oxidation. Oxidation of alcohol. If we oxidize alcohol in presence of KMnO4, potassium permanganate, or potassium dichromate in acidic medium, that is our H2SO4, we get aldehyde and water. Now in this process we need to remove this aldehyde because it can get further oxidized in acids. So we need to remove this aldehyde to stop the further oxidation. Collins reagent also acts as oxidizing agent. We take chromium trioxide pyridine complex This is chromium trioxide pyridine complex in the presence of dichloromethane, which act as solvent, and we get aldehyde. For ketones, we need to take secondary alcohol in the presence of same oxidizing agent KMnO4 or K2Cr2O7 in acidic medium. We'll get ketone. There's one more, open your oxidation. Open or oxidation is done for ketone. For getting ketones, we'll take secondary alcohol in excess of acetone and in presence of aluminium tertiary butoxide, that is CH3 thrice CO. This is aluminium tertiary butoxide in excess of acetone. We'll get ketone. Here ketone cannot get oxidized further, so we need not to remove ketone as formed. The second method from alcohol is by catalytic dehydrogenation. Primary and secondary alcohol, when heated in presence of copper, we take copper gas and we'll get aldehyde and ketone. The temperature is taken 573 Kelvin and we'll get aldehyde and hydrogen gas will remove. If we take secondary alcohol, we'll get this is the better method because the compound formed are not further oxidized. Now these are the methods from alcohol, and the next method is from acid chlorides. Acid chlorides are RC double bond O Cl. We take palladium and barium sulfate as our oxidizing agent and we get aldehyde and hydrochloric acid. This catalyst is partially deactivated by addition of sulfur or quinoline to stop further oxidation. Aldehyde can be oxidized in acid. To stop this reaction, we need to add sulfur or quinoline. This reaction is called as Rosenmund reaction. For ketone, we take cadmium dichloride and we get cadmium chloride is removed. Dialkyl cadmium is used to make ketones from acid chlorides. This alkyl cadmium is if we take Grignard reagent and acid chloride, it gives acetone, but this again on reaction with Grignard reagent will give alcohol To avoid this, dialkyl cadmium is used and it is formed by this reaction. By the reaction of Grignard reagent and dialkyl cadmium, we get this dialkyl cadmium . So to stop this reaction, we need to take dialkyl cadmium instead of this Grignard reagent. Next method is from fatty acids. Calcium salts of fatty acids on dry distillation or pyrolysis, that is heating, will give aldehydes or ketones. This is our calcium salt of fatty acid, and another salt of fatty acid. This is calcium acetate, and this is calcium formate. Will give aldehyde on dry distillation and calcium carbonate. Here formaldehyde and acetone also formed. Ketones are formed by dry distillation of fatty acids alone. There is no need to take fatty acid, formaldehyde, calcium salt of formaldehyde. Only fatty acids will give ketones. Here we are taking calcium salt of acetic acid. This is on heating will give ketone, that is acetone and calcium carbonate. Mixed ketones are also formed if we take mixed fatty acids. If we take calcium salt of acetic acid and calcium salt of propanoic acid will give mixed type of ketones, that is our ethyl methyl ketone and calcium carbonate will be removed. Next method is by passing vapors of fatty acids on manganese oxide. If we take formic acid and this is our manganese oxide at the temperature of 575 Kelvin will give formaldehyde plus water and carbon dioxide gas will remove. If we take acetic acid and formic acid, it will give acetaldehyde and if we take 2 molecules of acetic acid alone, this reaction will give acetone. These are the methods from fatty acids. Now the next method is from alkynes. From alkynes, there are two methods. First is hydration of alkynes. Hydration of alkyne will give aldehydes. This reaction is done in presence of dilute H2SO4 and mercuric sulfate at the temperature of 343 Kelvin. Ethyne will give acetaldehyde, and if we take propine, then it will give acetone. The next method from alkyne is on hydroboration. Hydroboration of non-terminal alkynes will give acetone. We are taking half molecule of hydroboron, and it will give complex of boron, which on hydrolysis will give, in alkyne medium, will give this intermediate, and it will change into acetone, butanone. So hydroboration of non-terminal alkynes will give ketones. The next method is reductive ozonolysis of alkene. If we take alkene and react it with ozone, it will give this type of compound, which is called ozonide. This ozonide on hydrolysis in presence of zinc will give aldehyde. This zinc is used to remove H2O2, that is hydrogen peroxide, and hence to stop further oxidation. From alkyl nitriles, the next method is from alkyl nitriles. This reaction is done in presence of tin chloride and dilute HCl. It will give imine product, salt of imine, HCl. This on hydrolysis will give aldehyde and ammonium chloride. This type of reduction is called Stephen reaction. Next method from alkyl nitrile is this is done in presence of diisobutyl aluminum hydride in presence of acid will give aldehyde. This is acid hydrolysis of alkyl nitrile in presence of diisobutyl aluminum hydride will react on alkyl nitrile and give aldehydes. The next method is from esters. The same reagent will take diisobutyl aluminum hydride on acid hydrolysis will give aldehyde. Now preparation of aromatic aldehyde and ketones. First is oxidation of alkyl benzene. If we take toluene in presence of chromium oxide in presence of anhydride, it will give benzyl diacetate. And this on hydrolysis will give benzaldehyde and 2 molecules of acetic acid. In this reaction, the benzaldehyde formed is trapped by acetic anhydride to form benzyl diacetate, and hence further oxidation of benzaldehyde to benzoic acid is prevented. So it's essential to add acetic anhydride to prevent further oxidation. Toluene in presence of CrO2Cl2 chromyl chloride and carbon tetrachloride will also give benzaldehyde. It will give an intermediate complex which on hydrolysis will give benzaldehyde. This reaction is called Aldehyde reaction. Next method to form aromatic aldehyde ketones is by Friedel-Crafts reaction. Acetyl chloride or any alkyl chloride on reaction with anhydrous aluminum chloride in presence of anhydrous aluminum chloride will give ketone. Next method is by Gattermann Koch reaction. In presence of aluminum chloride in acidic medium, it will give benzaldehyde. So here the formylation of benzene ring is occurred by carbon monoxide, and it makes benzaldehyde. The next method is side chain chlorination. Side chain chlorination of benzene ring is done in presence of sunlight and chlorine, and it will give benzyl chloride, and then on hydrolysis it will give benzaldehyde. This reaction is very useful as it is commercial method to make benzaldehyde. From Grignard reaction, this is our Grignard reagent. This Grignard reagent on reaction with cadmium dichloride will give dialkyl cadmium. This dialkyl cadmium will react any aromatic chloride dialkyl cadmium, and it will give ketone, aromatic ketone. If we take CN and dibenzyl cadmium, that is C6H5CH2, and it's cadmium, dialkyl cadmium, it will give aromatic ketone, and cadmium chloride will remove. The next method is from alkynes. Alkynes on hydroboration. In presence of tetrahydrofurane, in alkyne medium will give aldehyde or ketone. This alkyne in presence of dilute H2SO4 and HgSO4 at the temperature of 333 Kelvin will also give aldehyde or ketone. So from alkyne we can get aldehyde or ketone by hydroboration or by the reaction of sulfuric acid or HgSO4. Physical properties of aldehydes and ketones. First, physical state. Lower members of aldehydes up to C4 are colorless volatile liquid. Higher members are solid. C4 and onwards are solid with fruity smell. With fruity smell. But lower aldehydes have unpleasant smell. But all ketones have fruity smell or fruity or pleasant smell. Boiling point. Second is boiling point. Boiling point of aldehyde and ketones are greater than hydrocarbons. Why it is greater? It is because of the polar nature of carbonyl group. Due to this polar nature, there is strong intermolecular dipole-dipole moment, dipole-dipole interaction. Due to this dipole-dipole interaction, its boiling point for aldehydes and ketones are higher than hydrocarbons. But their boiling point is less than alcohols, because in alcohol there is strong hydrogen bonding. In alcohol, strong hydrogen bonding is there, and this hydrogen bonding is much more than dipole-dipole interaction of carbonyl groups. So it is greater in alcohol. Boiling point of ketone are greater than aldehydes. Boiling point of ketones is greater because of two alkyl groups are there, which is electron repelling group. So the boiling point of ketones are greater than aldehyde. Next physical property is solubility. Up to C4 aldehyde and ketones are soluble in water. The solubility in water is because of strong hydrogen bonding between water and carbonyl group. Solubility decreases on increase of molecular weight. Why it decreases? Because on increase in molecular weight, there will be non-polar group. This non-polar group, alkyl group, increases, and it will protect the hydrogen bonding between water and this carbonyl group. Aromatic carbonyl compounds are less soluble than aliphatic compound. But all carbonyl compounds are fairly soluble in organic solvents. Organic solvents such as ether, benzene, and chloroform. All carbonyl compounds are fairly soluble in ether, benzene, chloroform, and other organic solvents. Next is chemical properties. Due to polarity of carbonyl carbon, it is electrophilic in nature. That means it will attract the electrons, and oxygen is nucleophilic. Hence, it will work as Lewis base, and the carbon will act as a Lewis acid. So these compounds will undergo nucleophilic addition reaction. Now we'll study acidity of alpha hydrogen atom. Why alpha hydrogen atom is acidic? It is because of strong electronic withdrawing effect of carbonyl group. And after this electron withdrawing effect, the its conjugate base will be resonance stabilized like this. This bond will go here, and this bond will shift. These electrons will shift in between carbon and carbon. So after attack of any nucleophile, this ion is resonance stabilized, so it will be more stable. Now we'll see attack of nucleophile. This is a carbonyl group. This is charge, negative and positive. The structure of this carbonyl group is trigonal planar. And this carbon is sp2 hybridized. when any nucleophile attacks, what happens? It will attack on this carbon because it is electrophile. After attack of nucleophile, the structure of this carbon will be like this. Here it is trigonal planar structure, and now it will be tetrahedral shape. And the hybridization state will be sp3. It will change from sp2 to sp3. It's a slow step. Attack of nucleophile on carbonyl group is a slow step. After this, the proton will attack. It's a fast step, and it will become like this. This compound is also tetrahedral shape, and the hybridization state is sp3. This alkoxide ion is an intermediate, and this is our final product. Now we'll study relative reactivity of aldehyde and ketones. Which factors will affect the relative reactivity is first electron releasing effect. Electron releasing effect is plus I effect. Who will show plus I effect? The compounds who will give electrons will be having plus I effect. In ketones, there are two alkyl groups which push their bonded electron towards this positively charged carbon. So the decrease the magnitude of positive charge on it and make it less susceptible of nucleophile. These alkyl group will donate electrons, bonded electron. They will shift their bonded electrons towards this carbonyl carbon. So this carbon will become less susceptible for the attack of nucleophile. So the reactivity of aldehyde and ketones will be less reactive as compared to aldehydes. These ketones will be less reactive towards nucleophile as compared to aldehydes. Next is steric effect. How steric effect will affect on the reactivity of aldehyde and ketones? See, here is two alkyl groups, and in aldehydes this may be alkyl group or hydrogen, and the second will be, of course, it will be hydrogen. So in ketones there are two bulky alkyl groups. These two bulky alkyl groups will hinder the attack of nucleophile on this carbon, whereas in aldehydes only there is only one alkyl group is there. So this is more reactive as compared to this ketone. And in formaldehyde only two hydrogen atoms are there, no alkyl group is there. So this formaldehyde will be more reactive towards nucleophile as compared to other aldehydes, and these other aldehydes will be more reactive as compared to ketones. Reactivity decreases like this in aromatic compounds. Aromatic aldehydes as benzaldehyde will be less reactive than other aldehydes. The reason is same. There's a big benzene ring that will protect the attack of nucleophile on this carbon. And because of resonance stabilization of aromatic ring, this is our benzene ring. This is our benzaldehyde. This is carbonyl group. What will happen in resonance? This bonded electron will shift on this oxygen, and this will shift here. It will make like this. It will become double bond. This will be single bond. This is negative charge. One structure is this, and the positive charge will come here. The next is this bonded electron will shift here, and positive charge will come here. And next structure, this bond will shift here, and the next this will shift here, so it will become again single bond, and this negative charge will shift here. So these are the our resonance stabilization states of benzaldehyde. So this is benzaldehyde will reactivity of benzaldehyde towards nucleophile will become less as compared to aliphatic aldehydes. So the reactivity order of aromatic carbonyl compounds will be like this. Here it is one benzene ring, so because of resonance stabilization its reactivity will be less. But in this compound there's a benzene ring and there's one alkyl group, so steric effect and plus resonance effect of this benzene ring will become more as compared to in this compound benzaldehyde, so it will be less reactive. And in C6H5 there are two benzene rings that will affect the steric effect and plus resonance effect, so it will be less reactive as compared to this, so reactivity order will decrease. Now we'll study nucleophilic addition reaction. Attack of nucleophile. The first reaction is addition of hydrogen cyanide. Carbonyl group will react with hydrogen cyanide, will take hydrogen cyanide. It will come from hydrogen chloride plus sodium cyanide, that will make hydrogen cyanide in vitro, and it will form cyanohydrin. Second is reaction with sodium bisulfite. sodium bisulfite. First nucleophile will attack. This is our nucleophile, SO3H. Then proton transfer. It will become like this. Now sodium ion will attack. This is a reversible reaction, and it will make bisulfite compound. This is bisulfite compound. Now third is addition of Grignard reagent. What is Grignard reagent? This is RMGX. First attack of nucleophile, then electrophile. And this will, after hydrolysis, will make an alcohol. And the byproduct is NH. In this reaction, formaldehyde will give primary alcohol. This is our primary alcohol, and other aldehydes will give secondary alcohol. This is our secondary alcohol, and ketones will give tertiary alcohol because two alkyl groups are attached already and one carbon, so it is tertiary alcohol. Next reaction is addition of alcohols. When we react carbonyl group with the alcohol in presence of dry HCl, it will make hemiacetal. But this reaction does not stop here only. It will react further. Will take another molecule of alcohol and it will make ketanes, acetals. This is hemiacetal and this is acetal. And the byproduct is water. The next reaction is addition of ethylene glycol. This is our ethylene and glycol. In presence of dry HCl as well as, it will make this type of compound, a cyclic compound, and this will called cyclic ketane. Alcohols, addition of alcohols on carbon compounds will make hemiacetal and acetal, and with the help of dialcohol, this will make cyclic ketone. First we studied addition of nucleophile. Now second we will study nucleophile addition elimination reaction. Nucleophilic addition RMGS, this is Grignard reagent, and it will react with carbonyl group like this. Attack of nucleophile first, and this product on hydrolysis will give alcohol. And the byproduct is formaldehyde will give primary alcohol on addition of Grignard reagent, but other aldehydes will give secondary alcohol. This is our secondary alcohol, and ketones will give tertiary alcohol. Addition of alcohols. We'll take a carbonyl group compound, and the alcohol, when in presence of dry HCl, will give this type of compound, which will called hemiacetal. This reaction does not stop here only, but other alcohol group will react furthermore with this hemiacetal group. So it will make this type of compound. This is called acetal. This is hemiacetal, this is acetal. Carbonyl compounds will react with diols in presence of dry HCl. It will make this type of compound. This is a cyclic compound, and this is called cyclic ketane. So carbonyl compounds on reaction with alcohol will make hemiacetal and acetal, but with diols it will make cyclic compounds. Now we were studying nucleophilic addition reaction. Now we'll study nucleophilic addition elimination reaction. Now first we'll study, this is our carbonyl group compound. This will react with ammonia. On heating it will make imines. We can take other compounds as well as hydroxylamine on reaction with carbonyl compound will make oximes. Carbonyl compound will react with hydrazine. What is hydrazine? NH2. NH2. It will make oximes is C double bond NOH. Water will remove, and this will make hydrazine. Hydrazone. Hydrazine will react with carbonyl compounds and make hydrazone. With phenylhydrazine, it will make phenylhydrazone. Two four six dinitro 2,4 dinitro phenylhydrazine on heating with carbonyl compounds will make hydrazones. This compound will be like this. This is 2,4,6 dinitro phenylhydrazine, and this is our final product, hydrazone. Carbonyl compounds on reaction with semi-carbazide will make semicarbazone. Formaldehyde react with ammonia and make this type of compound. We'll make another, and this CH2, CH2, CH2N, this is N, CH2, CH2, N, this is our hexamethylene. See, 1, 2, 3, 4, 5, 6 methylene group is there, and four amine group, 1 2 3 4, so it is called hexamethylene tetramine. It is also called urotropin. This urotropin is used in making RDX. Now reaction with PCl5. Carbonyl compounds on reaction with phosphorus pentachloride will make dichlorocompounds. Carbonyl compounds on reaction with thionyl chloride in presence of pyridine will also make dichlorocompound. This is jam dihalide compound. Jaminal. Jam means jaminal dihalide compounds. Now, third type of reaction is reduction of aldehydes and ketones. Reduction of aldehyde and ketones to alcohol. Carbonyl compounds will reduce in presence of nickel or platinum or palladium, and it will make alcohols. This reaction can be done in presence of lithium aluminum hydride or barium hydride, and the product will be same. If we take ketones, it will make secondary alcohol. It will reduce in this. This reaction can be done in presence of aluminium isopropoxide, propanol. This is our aluminium isopropoxide. It will make secondary alcohol. This reaction is called Mirwin-Pondoff reaction. Now, reduction to hydrocarbon. These were reduction to alcohols, and the second is reduction to hydrocarbons. When we take ketones in presence of zinc amalgam, this is zinc amalgam in presence of HCl, it will make alkanes and water. This reaction is called Clemmensen reduction. When carbonyl compounds react with hydrazine, it will also reduce and make hydrogen. This is our hydrogen. This hydrogen on heating with KOH or ethylene glycol will make alkane and nitrogen will be removed. This reaction is called Wolff-Kishner reaction. When acetaldehyde or other ketones is heated with hydroiodic acid in presence of phosphorus at the temperature of 425 Kelvin, it will make alkanes as well as. Now reduction to pinecols. We have studied reduction of aldehyde and ketones to alcohol, then hydrocarbons, then now it is pinecol. No aldehyde give this type of reaction, only ketones. Will take acetone, 2 molecules of acetone will react in presence of magnesium amalgam in presence of water. It will make pinecols. Pinecols are nothing but diols. So this is two, 3 dimethyl 2,3 dimethyl 1, 2, 3, 4 butane and 2, 3 diols. So pinecols are diols and this compound 2, 3 dimethyl butane 2, 3 diols will be formed. It's a bimolecular reaction and two ketones are reacting with each other. Now next type of reaction is oxidation of aldehyde and ketones. And ketones. Aldehydes are easily oxidized to carboxylic acid containing same number of carbon atom as in parent aldehyde. The reason behind is presence of hydrogen atom on carbonyl carbon which can be converted into OH group without involving of any cleavage. It will make, there is no need of cleavage of this bond, so it will go and give oxidation reaction easily as compared to ketones. So aldehydes are oxidized by strong oxidizing agent such as KMnO4, K2Cr2O7, potassium dichromate, as well as weak oxidizing agents. Weak oxidizing agents are bromine water, and other reagents. So aldehyde acts as strong reducing agent uh, as compared to ketones. Now we'll study the oxidation of aldehydes in presence of tolerance reagent. Tolerance reagent is ammonical silver nitrate solution. This is our silver nitrate. This is H4OH ammonia solution. It will make silver hydroxide and NH4NO3 ammonium nitrate. This silver hydroxide will react ammonia solution again and will make a complex compound. This complex compound will react with aldehydes and will make ammonium salt, and silver will deposit. It will give precipitate. This will give a shiny appearance. So this test is called silver mirror test. We can see a thin lining of silver, shiny silver. So this test is called silver mirror test. Next oxidation reaction is with Fehling solution. Fehling solution is alkaline solution of copper sulfate. Containing sodium potassium tartrate. This is called Rochelle salt. So the reaction will happen like this. This is our alkaline solution of copper sulfate, and on heating it will give sodium salt and will get precipitate of cuprous oxide. It will be of red color PPT. So this reaction is called reduction of Fehling solution. Now next is reduction of Benedict solution. What is Benedict solution? This is alkaline copper sulfate containing citrate ion as complexing agent, and the reaction will occur like this. This is our cupric hydroxide, and it will reduce in cuprous oxide. It will give red precipitate and the salt of acid. Now Tollens test and Felling's test and Benedict tests are only given by aldehydes, not by ketones, because these are weak oxidizing agent and not capable to oxidize aromatic aldehydes and ketones. So this test will given only by aldehydes, not by ketones. Now we'll see the oxidation of ketones. For oxidation of ketones, we need strong oxidizing agent as what are strong oxidizing agents? Concentrated nitric acid, potassium permanganate, and with H2SO4 or potassium dichromate with H2SO4. Why we need strong oxidizing agent for oxidation of ketones? Because it will involve cleavage of bond between carbonyl carbon and alpha carbon on either side. It will involve the cleavage of this bond or this bond. So it will give a mixture of acids. It will give mixture of carboxylic acid and will get the smaller number of carbons in that carboxylic acid as compared to our parent carbonyl compound. The reaction will happen like this. It will make formic acid and acetic acid. Now there is a rule for the oxidation of ketone. This is called Popoff's rule. What is Popoff's rule? If we take any carbonyl compound and on oxidation of this carbonyl compound will get a mixture of acids. So the point of cleavage in this compound is such that this keto group will stay with smaller alkyl group as compared to larger alkyl group. So it will go preferably this side and it will give a mixture of acids. If it breaks from this side, it will give formic acid plus butanoic acid. This is our formic acid and this is our butanoic acid. And if the cleavage happens on this side, this is our A side and this is our B side, this is B and this is A. So then we will get this acid and this. So acetic acid and propanoic acid. So we'll get mixture of these four acids, but this will be a minor product according to Pophoff's rule, and this will be major product, because this carbon will go on the lower alkyl side. Here it is only one carbon in this alkyl side, and here it is 3 carbons, so it will go this side and will make acetic acid and propanoic acid. Now the next type of reaction is haloform reaction. This reaction is given by this type of compounds, by ketones or aldehydes, whatever, or maybe alkyl group may be hydrogen or any alkyl group, methyl, ethyl, whatever, and aromatic ring also. So this will give sodium halides, sodium oxyhalides. Sodium oxyhalides will be come from sodium hydroxide and halogen, and it will give haloforms. This is our haloform, and we'll get sodium hydroxide as well. Here X may be chlorine, bromine or iodine. Now reaction with alkalis. Now reaction with alkalis, in this section first is aldol condensation. Only those aldehydes or ketones which have alpha hydrogen atom will give this kind of reaction. It will occur in presence of dilute alkali. We'll take dilute NaOH, and it involves the formation of bond between carbonyl carbon and the bond between carbonyl carbon of one molecule and the alpha carbon of another molecule. So this bond will be formed CH2CHU. This compound is called aldol, and this is will number 1, 2, 3, 4. So this alcohol group is present on third carbon. So this is 3 hydroxy and 4 carbon is there, so butanol. This is 3 hydroxybutanol or acetaldol. Acetaldol. Aldol name comes from two functional group. One is aldehyde. Here this is one aldehyde and the other is alcohol. So aldol, all from alcohol, and aldehyde, L from aldehyde. The reaction is reversible, but equilibrium, this reaction is C will take two molecules of acetone in presence of dilute and alkali, will take any barium hydroxide, and this type of compound will be formed. And this is diacetone alcohol. Or we can number 1, 2, 3, 4, 3 hydroxy. No, this will get number 1, 1, 2, 3, 4, 4 hydroxy, four methyl, pentane, pentane, 2 on, 1, 2, 3, 4, 5, so 5 for pentane for 5, and the ketone group is present on second carbon, so this is 2 on. Now this reaction is reversible, but equilibrium favors the formation of aldol or ketone. The yield of ketones are very poor as compared to aldols because of steric factor. Here two alkyl groups are protecting to occur this reaction as compared to aldehyde. There is one hydrogen atom in both the molecules, so this reaction will happen very easily as compared to the formation of ketone. The ketones will give, on heating, it will give elimination reaction, removal of water from here, and it will make this type of compound. Water will be removed. This is called macetyl oxide. Or alpha beta unsaturated ketones, or we can give IUPAC name also. So we'll number from here 1, 2, 3, 4, 5. So 4 methyl, 5 carbon compound is here, this. So 5 pentane, 4 methyl pent, and this is alkene. So the position of double bond is on third position. So 3 ene, and the position of ketone is on second. So 2 on. So it will be named as 4 methyl pent 3 ene 2 on, or we can say macetyl oxide. Mechanism of aldol reaction is this is our carbonyl compound. The hydroxide ion will attack on this. This is the first step, and it will take away this hydrogen from here, and it will make this ion, and water will be removed. Attack of hydroxide to abstract proton from alpha carbon. This is our alpha carbon attached to the carbonyl group to form carbon ion. Now the second step, attack of nucleophile. This will go here, this bond will shift on this, and it will make and this bond will be formed. This is our another molecule which has been attached here, and the third attack of nucleophile on electrophilic carbonyl carbon of second aldehyde molecule to form an alkoxide ion. This is our alkoxide ion, and a new bond between carbon and carbon is formed. Now in third step, this alkoxide ion will abstract a proton from water, will come from water, and it will form a new compound this proton will attach here, this proton, this is proton, and this is our new compound, and hydroxide ion will be removed, will be formed for the next reaction. This is aldol condensation. Now we'll study cross aldol reaction or crossed aldol condensation. It will be carried out in between two different aldehyde or ketones. We can take different type of two aldehydes, different type of ketones, or one aldehyde and one ketone. In for this reaction, it is compulsory that both the compounds should have at least one alpha hydrogen. Alpha hydrogen atom is a must, and it will give a mixture of products. We'll take acetaldehyde and CH3, CH2, CHO, 3 carbon compound, propanaldehyde, and heating with dilute alkali, it will give this product will be formed by self-aldol condensation. Self-aldol condensation of acetaldehyde. So two molecules of acetaldehyde will make this compound. This is but 2-enal, and will get CH2. This product we will be getting from propanaldehyde, and the aldol will be formed, and that aldol will give remove that one molecule of water, and it will become 2-methyl pent for 5 2-enal. Both the products are the result of self-aldol condensation. This is the self-aldol condensation of acetaldehyde, and this is from self-aldol condensation of propanaldehyde. Now from cross-aldol condensation, we'll get one product, and the other product will be this. This is 2-methyl. This is 2-methyl butenol, and this is pent-2-enol. So this is self-aldol condensation, and this is cross-aldol condensation. In cross-aldol condensation, in this product, we are taking first this alpha hydrogen, and for the second product we are getting this alpha hydrogen. So we are getting if we are taking this alpha hydrogen for the condensation, we'll get this product, and if we are taking this alpha hydrogen, so this alpha hydrogen, then we will get this product. Now third is Cannizzaro reaction. This type of reaction is given by only by those aldehydes which do not have alpha hydrogen. For this reaction, alpha hydrogen atom should not be there. It will undergo self-oxidation and reduction reaction on treatment with concentrated alkali. We'll take formaldehyde, there is no alpha hydrogen atom, and the second molecule, in presence of strong alkali, we can take potassium hydroxide or sodium hydroxide. It will give one molecule of alcohol and the salt. So this is going reduction. The one molecule is undergoing in reduction, and the other in oxidation. So one molecule will give acid on oxidation, and the other molecule will give alcohol on reduction. Now cross Cannizzaro reaction. Reaction by two different aldehydes, but both the aldehydes should not have alpha hydrogen, will give different type of products. But if one of the aldehyde is formaldehyde, the reaction yields exclusively formate and alcohol of another aldehyde. If we take benzaldehyde, which is not having alpha hydrogen, and the formaldehyde, which is also not having alpha hydrogen, in presence of strong alkali, on heating, it will give benzyl alcohol and formate, sodium formate. So if the one reagent, one aldehyde is formaldehyde, the yield will be the acid of formaldehyde, and the another aldehyde will go on reduction and it will give alcohol. So preferably we will get this product as compared to the acid of this and the alcohol of formaldehyde or methyl alcohol. Next reaction is Next type of reaction is electrophilic substitution reaction. Aromatic aldehydes and ketones undergo electrophilic substitution reaction in which the carbonyl group act as deactivating and meta-directing group. We take this benzaldehyde, and if we take nitric acid in presence of concentrated H2SO4 sulfuric acid, here the carbonyl group is deactivating group and meta-directing, means the attack of electrophile will on meta position of the carbonyl group. So this is our carbonyl group, this is ortho position and this is meta position. So the attack will happen here and will get meta nitro benzaldehyde. This is meta position, meta nitro benzaldehyde. Now miscellaneous reaction, different types of reactions. First is formation of frones. Three molecules of acetone will take 3 molecules of acetones, will write like this, and the third is here. In presence of dry HCl, 2 molecules of water will be removed here, and the one is from here, and it will make frones. This compound is called frone. Now the next is formation of mesitylene. Three molecules of acetone on refluxing with concentrated sulfuric acid will make mesitylene, and 3 molecules of water will be removed, and this is our mesitylene. Action with Schiff reagent. It is an aqueous solution of magenta or pink colored rosanilene hydrochloride hydrochloride which has been decolorized by passing SO2. So on passing with SO2 it will be decolorized, but with reaction with aldehyde, the pink or magenta color will reappear. We can differentiate aldehyde and ketones by this reaction because ketones does not give this kind of reaction, means on reacting with Schiff reagent it will not change the color. So we can differentiate between aldehyde and ketones with the help of Schiff reagent. Now the next type of reaction is with potassium cyanide, alkali potassium cyanide alkaline potassium cyanide on heating will give this kind of compound, which is called benzoin. So this reaction is called benzoin condensation. Now reaction with chloroform. This is our chloroform, CHCl3. We'll take acetone and in presence of alkali we are taking potassium hydroxide and it will form chloritone. This compound is called chloritone. Now we can differentiate between aldehyde and ketones. We will taste with first Schiff reagent. It will give pink or magenta color. And ketone, it will not give. Now next, Fehling solution. It will give red precipitate, but ketone will not give the red precipitate, or it will not undergo this reaction. Tollens reagent, it will give silver mirror. Ketone will not give this reaction. 2,4-dinitrophenylhydrazine, it will give orange yellow crystals. With melting point characteristics of individual aldehydes, and this will give orange, yellow or red crystals with melting point characteristics of individual ketones. and with alcohol in presence of dry HCl forms acetal and it will form ketones. It will not form ketones. This reaction will happen very easily and it will not happen easily. Carboxylic acid. Our next topic is carboxylic acid. Organic compounds containing this type of group is called carboxylic acid. This group has acidic nature, so this is called acids. This group has both the carbonyl group and OH group. So we'll take carb from this and oxyl from this and we'll call oxyl from hydroxyl group and carb from carbonyl. Carb from carbonyl and oxyl from hydroxyl. So this will be called carboxylic group. This carboxylic acid may be aliphatic or aromatic. Depends if this acidic group is attached to alkyl, then it will be alkyl carboxylic group, aliphatic carboxylic group, and if the acidic group is attached to any ring, it will be called aromatic carboxylic acids. Depending upon the number of carboxyl group, it may be classified as mono, di, tri, or polycarboxylic acid. In acetic acid, we can see only one carboxylic group is there, so this is monocarboxylic acid. If we take this compound, this is oxalic acid. There are two carboxylic groups, so this is dicarboxylic group. And in citric acid, this is our citric acid, which have 3 carboxylic group, so it is called tricarboxylic acid. And if this carboxylic group is present on a benzene ring, so this is aromatic carboxylic acid, and we'll say benzoic acid. Now we'll name the name of carboxylic acid come from hydrocarbons. When we remove hydrogen atom from this hydrocarbon and add one carboxylic group, it will make carboxyl group, and will name this is, if we are taking alkane, it will become alkanoic acid. General formula for aliphatic monocarboxylic acid is given by Cn H2n plus 1 COH, or CnH2nO2. This formula is applied same for esters. Means acids, carboxylic acids and ester have the same formula, same general formula. So esters and carboxylic acids are functional group isomers. Or we can say esters and carboxylic acid show functional group isomerism. Some aliphatic monocarboxylic acids are known as fatty acids. Higher members C12 to C18 like palmitic acid, its formula is C15H31COOH, and stearic acid that is C17H35COOH. These acids exist in natural fats as esters, and on hydrolysis we can get these acids, so these are called fatty acids. Common name for carboxylic acids are derived from the source from which they were first isolated. So for formic acid, it is isolated from ants, that is formica, so it is called formic acid. Acetic acid is isolated from acetum, that is vinegar, so it is called acetic acid. Position of substituents. For trivial name is given by Greek numerals. This is our functional group, carboxylic group. The carbon attached to this group is named as alpha. The next is beta. Then next is gamma. So if we have any substituent will give the position accordingly, alpha, beta or gamma. For IUPAC name of carboxylic acid is given by alkane, and it will be called alkanoic acid. The longest chain will be selected. Here the longest chain is here 1, 2, 3, 4, 5, and in this longest chain the carboxyl group will be always be given number 1. We can't start from here, or we need to take this carboxyl group first and we'll give it preferably no, always number 1. So, and the position of other groups and substituents are given by numbers accordingly. We'll give it 1, 2, 3, 4 and 5. This is our longest chain. Here it is 4 carbon chain, and here it is 5 carbon chain. So we'll select this longest chain, and this group will be given number 1, and the number of carboxyl group is indicated by the prefix di, tri, etc. to the term oic, and position is indicated before the prefix. So the aromatic alcohols are named as derivatives of parent benzoic acid. This is our benzoic acid, and the other aromatic carboxylic acid will be given name as a derivative of this benzoic acid. If we will take some examples. Lactic acid. Now this is our longest chain. We'll give number 1, 2 and 3. The hydroxyl group is present on second position. So 2-hydroxy, 3 carbons are there. Propane, propanoic acid. Oic for carboxyl group. And for this aromatic compound, its trivial name is salicylic acid, and the IUPAC name will be derived from 2-hydroxy benzoic acid or 2-hydroxy benzene carboxylic acid. Now we'll study method of preparation. For unsaturated acids, we'll name its common name is acrylic acid, and the IUPAC name will be, there are 3 carbons on this chain, so prop for 3. The position of double bond is on second, so prop 2-ene and oic acid, prop 2-ene oic acid. Now method of preparation for acids. Carboxylic acid, first is by oxidation of primary alcohol. It's a very easy method. We'll take primary alcohol and will oxidize in presence of KMnO4 or K2Cr2O7, that is potassium dichromate, or dilute H2SO4. We can take any of them and it will give carboxylic acid and water. The second method of preparation is oxidation of aldehydes. Aldehydes on oxidation in presence of the same potassium dichromate or Fehling or Tollens reagent, as we have read in the previous section. it will give acid. The third method is oxidation of methyl ketone. Oxidation of methyl ketone is done in presence of hypohalite solution. This is our hypohalite solution. It will give salt and iodoform. This on hydrolysis in presence of hydrochloric acid, this sodium salt will give acid and sodium chloride. Acid formed in this reaction has one carbon atom less as compared to its parent ketone. So we will get one carbon atom less acid. And the next method is from alkyl cyanide. Alkyl cyanide in reaction with water in presence of dilute acid or alkali will give carboxylic acid and salt. It is a very good synthetic method for preparation. And one more is from amides. Amides also undergo this type of reaction. Amides on heating with hydrochloric acid and water will give benzoic acid and its ammonium chloride. Next method is by carbonation of Grignard reagent. This is our Grignard reagent, and Grignard reagent in presence of bubbling carbon dioxide. Bubbling carbon dioxide is our dry ice, and in presence of ether it will give this compound, and again it is on hydrolysis will give acid and byproduct. Here acid formed is one carbon atom more than as compared to its parent, because we are adding carbon dioxide, so one carbon is extra here or more. Next method is from acyl chloride. From acyl chloride, this is our aromatic acyl chloride. Will take base pyridine or sodium hydroxide. This on reaction with water will give benzoic acid and hydrochloric acid. From acid anhydrides, the same type of reaction will happen. This is our anhydride, It will give benzoic acid and alcohol. Saponification. Esters on reaction on heating with aqueous alkali solution will give salt of acid plus alcohol. This salt of acid on acidification will give carboxylic acid. The sodium or potassium salt of higher fatty acids are known as soaps. So, alkaline hydrolysis of esters is called saponification. Now, next method is from sodium alkoxide and carbon monoxide. This is our sodium alkoxide and carbon monoxide on heating with high pressure will give sodium salt of acid. This is on reaction with hydrochloric acid will give our carboxylic acid plus water, and this is fatty acids. We can get fatty acid from this reaction. Next method is from olefins. Olefins are alkenes. We can get higher fatty acids from this method. We'll take ethylene, this on carbon monoxide and water at the temperature of 570 to 675 Kelvin, and phosphoric acid. We'll use phosphoric acid as a catalyst and it will give acid. This reaction is used in making higher fatty acids. The next method is from alkyl benzene. It's an industrial method. This is a toluene. Toluene on reaction with KMnO4 in basic medium or acidic medium will give benzoic acid. It is the industrial method to form benzoic acid. Now, physical properties of acids. We'll see first physical state. First, three aliphatic acids, that is C3, these are colorless, liquids, colorless liquids with pungent smell, sharp smell. And the next six compounds, C6, next six compounds from C9 till C9, these are oily liquids, with rancid butter smell, These compounds till C9, these are oily liquids with rancid butter smell or odor, and higher members are colorless, odorless, they're having no smell, and waxy state is waxy solids. Lower members are liquids and higher members are solid in state. Benzoic acid is crystalline solid. It is found in crystalline solid state. Now the second physical property is solubility. First four members are soluble in water. Why these are soluble in water? It is because of intermolecular hydrogen bonding with water. This is our acid, so it is having negative charge, partial negative charge. It is having partial positive charge. It is also having positive charge, negative charge. This is negative charge. So in water, the hydrogen bonding between acid and water is there. So these compounds are soluble in water, but in higher compounds, this alkyl group, the nature of this alkyl group is non-polar and its size is very bigger. So the higher compounds are less soluble or insoluble. Solubility is very less or insoluble. Boiling point. Boiling point of acids are very high because of intermolecular hydrogen bonding. Acids are present in dimeric structure because of hydrogen bonding. This is our hydrogen bonding. Because of this dimeric structure, the effective molecular mass is just double. It becomes just double. So the boiling point of acids are greater as compared to alcohol because of the hydrogen bonding, and in acid the acid is more polar than OH in alcohol because of this electron withdrawing nature effect of this carbonyl group. This is carbonyl group which has electron withdrawing group in acids, and it is not there in alcohol. So the boiling point of acid is greater as compared to acids. Now the structure of carboxylic group. In carboxyl group, this carbon is in sp2 hybridization state, and the atoms carbon, oxygen and oxygen. This oxygen is found or lie in one plane, and the bond angle between C double bond O and O double bond C and oxygen is 120 degree and are found in one plane. So this carboxyl group carbon, and this carboxylic carbon is less electrophilic than carbonyl carbon in aldehyde and ketones. This is due to the delocalization of lone pair of electron. It is like this. The delocalization of lone pair of electron is like this. These are lone pair of electrons. So -5, because this bond will shift here. It has been shifted here, so it will have positive charge. Now this lone pair of electron will shift here, and it will make it will get positive charge because shifting of this lone pair electron in between carbon and oxygen, it will get positive charge, and it is having 3 lone pair of electrons, so negative charge. Due to this delocalization of lone pair of electrons from the oxygen in hydroxyl group, this structure is more stable. Now, the chemical properties. First, we'll study acidic nature. Carboxylic acid dissociates in water to give resonance stabilized carboxylate anions and hydronium ions. This is a carboxylic acid. In water, it will give hydronium ions, and the resonance stabilized carboxylate ion. This bond will shift here and it will make another structure. It will get minus charge, and this bond will shift here. This will shift here. It will make this. This bond is shifting here and this charge will shift here. So we'll get another structure which is same. Means this bond is partially double bond and it will be having negative charge. So these acids are weaker than mineral acids but stronger than alcohol and simple phenols. So we can say the strength of acids, mineral acids are very strong as compared to carboxylic acid, and from alcohol and phenols. The strength of acids are like this. Electron withdrawing group stabilizes the carboxylate anion and strengthens the acid through the delocalization of the negative charge through the inductive effect or resonance effect. An electron donating group decreases the acidity by delocalizing the conjugate base. Now, the next factor affecting the acidity of carboxylate ion is distance between carboxyl group and electron donating withdrawing group. Electron withdrawing group increases. Electron withdrawing group stabilizes the carboxylate anion and strengthens the acid through the delocalization of this negative charge through the inductive effect or resonance effect. And electron donating group decreases the acidity by destabilizing the conjugate base. Distance between carboxyl group and electron withdrawing group, if it is increased, then acidic strength decreases. If it is like this, the distance between carboxyl group and electron withdrawing group is near as compared to this. So the acidic nature will be greater in this compound as compared to this. The next factor is if plus I effect increases, the acidic nature will decrease. If the substituent attached to the alpha carbon is more electronegative, then it will be more acidic in nature. See, if it is Here it is iodine, which is less negative, electronegative as compared to bromine, bromo group. It is more acidic as compared to this. And again fluoro group, if it is fluoro group attached to alpha carbon, it is much more acidic in nature. If the number of substituents, next factor is number of substituents, which is electron withdrawing group, are more, then acidic strength will be more. If we see the acidic nature, acidic order in these compounds, here 3 electron withdrawing groups are here, here are 2 and here is only 1, so the acidic nature will be greater in this compound and the acidic nature in this compound will be very less. Now we'll see the physical properties involving reactions involving OH bond cleavage. These are acidic properties. First we'll see if we react carboxylic acid with sodium, it will give its salt and hydrogen gas will be removed. If we are reacting it with the sodium hydroxide, again we'll get sodium salt of acid. If we react with sodium carbonate, we'll get sodium salt and water and carbon dioxide gas. If we take sodium bicarbonate, we'll get sodium salt, water and again carbon dioxide gas. These are the reactions involving cleavage of OH bond. Next is reactions involving cleavage of OH bond. This bond will be, first reaction is formation of acid chlorides. When we react carboxylic acid with phosphorus pentachloride or trichloride or thionyl chloride in presence of pyridine, we'll get acid chloride. Formation of acid bromide, acid amides. Formation of acid amide. When we react carboxylic acid with ammonia gas, we'll get ammonium salt, which on heating will give acid amides and water. Next reaction involving cleavage of RCOH bond is formation of esters or esterification. when we react acid with alcohol in acidic medium, it will give esters and water. Next is formation of acid anhydrides. When we react acid with in presence of P2O5 and on heating it will give anhydrides and water. Now the third type of reaction is reaction of complete S carboxyl group. First is soda lime decarboxylation. When we take sodium salt of acid and react with sodium hydroxide in presence of calcium oxide, it will give RH. Calcium oxide and NaOH will give soda lime, and sodium carbonate will be as byproduct. Second is coal-based electrolytic decarboxylation. When we take sodium salt, aqueous sodium salt of acid, it will ionize as an Na plus. At anode, we'll get alkanes and carbon dioxide gas will be removed. And at cathode, again hydroxide ion will be formed for further reaction. So from Kolbe electrolytic decarboxylation we can get alkane from acids. Now third one is dry distillation of calcium salt. When we take calcium salt of acid, we are taking two molecules, and on heating or dry distillation it will give calcium carbonate and acetaldehyde. Reduction. Acids on reduction in presence of copper chromate or lithium aluminum hydride will give alcohol. If it is reduced in presence of hydroiodic acid and phosphorus at the temperature of 500 Kelvin, complete reduction happens and will get alkane and iodine. Next type of reaction is Hunsdika reaction. This reaction is done in presence of inert solvent, silver salt of acid is reacting with bromine in presence of carbon tetrachloride, will get halides or bromide, and carbon dioxide will be removed and will get silver bromide. This reaction is called Hunsdika reaction. Now the fourth type of reaction of alkyl group of acids. First is oxidation. Oxidation is done in presence of hydrogen peroxide and alkyl group present at beta position is oxidized. This is our alpha, this is beta, and this is gamma. So the alkyl group at beta position is oxidized and we get alcohol, will get substituent alcohol group. This is our N-butyric acid and will get beta hydroxy butyric acid. See, this is our alpha carbon, this is our beta carbon. In this type of reaction only beta carbon is oxidized. So we are getting beta hydroxybutyric acid. When carboxylic acid is heated with selenium oxide, we get alpha keto acid and water and selenium is. This is our alpha keto acid. Next reaction is Hell-Vollard-Zielinski reaction or HVZ reaction, Hell-Vollard-Zielinski reaction. In this reaction, alpha halogenation of aliphatic acid is done. If we take acetic acid in presence of chlorine or bromine in red phosphorus, we get alpha halo acid. This reaction does not stop here only, it reacts further also and will get and again this product is found at the end. This reaction is called Hell-Vollard-Zielinski reaction. Now the next reaction is ring substitution in aromatic acids. This is electrophilic substitution reaction. reaction. In this reaction, COOH group, carboxylic group is deactivating and meta-directing. So, when we react benzoic acid in presence of nitric acid, concentrated nitric acid or concentrated sulfuric acid, and on heating it will give meta-nitrobenzoic acid. If we react benzoic acid in presence of bromine and heating with FeBr3, that is ferric bromide, will get meta-bromobenzoic acid.